So we're going to talk about the Gaussian mixture model stuff today. I will point out this is still kind of a work in progress. It's an active area of research, both for me and somewhat separately for Muyuan. So there are still a lot of active changes going on, but it's at the level now where you can use it for a bunch of things. So if you want to know more about the theory, the paper that was published last year in Nature Methods, that's a good source. Also, if you go to YouTube, I gave a talk at IPAM at UCLA recently. Great, exciting. So if you search for IPAM, and go to the Institute for Pure and Applied Mathematics playlists, all of the talks from that meeting that we had just a couple of weeks ago are available there. So you can see, so there, contextual confirmation variability. So anyway, so that IPAM talk is a pretty good background to the theory. The tutorial is also very much a work in progress. So if we look at standard tutorials, and then Gaussian mixture model, there's a link to the paper there. This tutorial is the one that we're looking at here, this GMM GUI tutorial. This is the tutorial that Muyuan wrote originally that accompanies the paper. There is a newer version of this that he's also prepared, but I don't think he's linked it in here yet, so you can get at it. This is the tutorial that we're supposed to be talking about today. So you can see that it's got some examples with the graphical interface here. Some of the stuff that you see in the GUI has already changed a little bit. So when I took this screenshot, this button existed and this button existed. Those are gone now. Anyway, there's been a couple of other sort of subtle rearrangements and stuff, but everything is more or less in the same place that you see it here. So what I thought we would do today is go over the results on a couple of different data sets. So the tutorial suggests that you might just use the subtomogram averaging results as input for this task. The ability to do anything with subtomogram averaging in the GMM is very recent, but it does actually work. So let me go to that project first. Let's see, which one is this? Yeast lamella. See, yeah, all right. So this is the results of the subtomogram averaging tutorial that we talked about last time. We run e2gmm.py. Should pop up this interface, and you get this warning about it being experimental. Right. And I talked about this a little bit last time, and I told you, that if you see these lines appearing there, that probably means you didn't refine it long enough. There's a couple of things that are different about applying this to subtomogram averaging data and single particle data. You have this sort of split with the single particle data. A particle is a particle. With the subtomogram averaging data, a particle is a particle, but a particle is also a tilt series. So from the perspective of the Gaussian mixture model, each tilt in the tilt series is sort of a particle. And what the GMM does is it takes all of the tilts in the tilt series and sort of considers them together as a single point in this embedded space. So if you get one that was processed processed longer. So if you see these lines here, that usually just means that you didn't refine it long enough, or that the perturbation that you imposed here was too small. If you look at one that was sort of trained more completely, then you see something more like this. All right, so let's just sort of take a look at this interface and how it's laid out. I think I may have said a little bit of this last time to just sort of prompt you sort of what to do. So the first step that you need to do here is to link one of your refinements to a Gaussian mixture model. You basically make a GMM sort of project within your project for one particular refinement run. You do that by hitting the new GMM button. I'm not going to do it right now because all of these steps take a couple of minutes to run. So you hit new GMM, and then it prompts you to select a folder. And when you select a folder, you have to select one of three types of folders. Let me go back here. So if it's a tomography project, you should have a folder named SPT000102, etc. So you could use an SPT folder, or if you're in a single particle project, you might have a folder named R3D000102, etc. That's if you use the new single particle refinement program. Then you'd have one of these types of folders. If you ran one of the, let me go to oops. Not sure if I only ran a new one here. Well, that's fine. Anyway, if you have one of the old style refinements, like a refine underscore number folder, run with E2 refine easy, those will also work with this. If you have a project from, say, Relion, and you want to look at that with the Gaussian mixture model, you have to import the Relion project into EMAN2. So there's a script E2 Relion to EMAN. I think that's it. Basically, you just give it the name of the star file. And of course, you need to make sure that the folder that you're in, the references in the star file point at images where they exist. So in other words, if you're in the folder with the star file, then the file names in the star file have to be valid file names from that point in your file system. The same would be true if you ran Relion. Anyway, if you run this program E2 Relion to EMAN, give it the name of the star file, then it should automatically go into the star file, pull out all the subsets of particles into similar micrographs and stuff like that. It'll make an EMAN2 folder, and it'll put all the normal EMAN2 stuff in there. After you've done that, you still need to run at least one round of the EMAN2, the new EMAN2 refinement. And you also need to run the CTF auto. You need to run E2 CTF auto.py. So that would make an EMAN2 folder. You'd CD into the EMAN2 folder. You'd run E2 CTF auto.py. And then when that ran, you'd need to run one round of refinement, either using the new or the old EMAN2 refinement program. And then you could run the GMM on the corresponding project. We at some point we'll set it up so you can just work directly with the star file and the orientations in the star file, but at the moment that doesn't work. Okay, so that allows you to sort of create one of these GMM folders. Once you've got a GMM folder, then you will do various runs inside the folder. And a run corresponds to sort of a particular choice of how many different Gaussians you want to put in different locations, what sorts of masks you want to use, what resolution ranges you want to do the Gaussian mixture model over, and that sort of thing. So this was a run that I did on the results of the subtomogram averaging tutorial. You can see over here, sorry, you can't see this, but my control panel for Zoom is kind of in my way here. Just trying to get it out of the way. There we go. Okay, so there are these controls here, which will control what appears in this window. Let's just start by looking at the neutral map. So this was the result of the single particle refinement. Okay, at whatever filtration, whatever it was originally done at. So this was sort of the starting point for the GMM. When we run the first step here, we're putting Gaussians into that, and that produces this neutral model. We can make the spheres a little bit bigger so you can sort of see them. The brightness of the spheres in the neutral model indicates their intensity. The black colored spheres are the spheres which were sort of the negative density spheres. They're supposed to be a little bit outside the density of the structure. and they exist as sort of reference points that can help the Gaussian mixture model figure out which direction things are moving and that sort of thing. Sometimes you won't see the black spheres because they're thresholded out. Sometimes you will. So if you don't see the black spheres, you can open the control panel. You can middle click here and you can open the control panel. And you can see here we've got neutral map, mask, dynamic model, neutral model. If we look at the neutral model and scatter plot, there's a threshold value you can use here. So you can see, oh, there. See, now I've thresholded out all of the black points. And if I lower it down, if you don't see them and you lower it even lower, then you should be able to make them appear. Whether you want to look at them or not, it's up to you. Let's see. Okay, so that's the neutral map and the neutral model. Once we've done the all right, so we come over here. The sequence of steps is you pick a filter resolution. So I'm going to go ahead and create a new run. I'm not going to actually go through all the steps here, but just to sort of demonstrate what happens. I'll just call this test. And this new run doesn't have anything in it yet. It's just sort of an empty container. So you can see that there aren't any points in our neutral model because we haven't generated any yet. So the first step we need to do is generate points for the neutral model. So you pick a resolution at which you want to do that. I'm just going to say 25. And hit the resolution button, and then that'll generate the points. You can see it also generated a filtered version of the map to show you what the map looks like at 25 angstrom resolution. If I open the control panel again here, I guess it's in the back. You can see that this filtered Gaussian map, there isn't a button for that down here. Probably should add one. So turn off the neutral map, and we can turn off the neutral model. Oops. Neutral map. There you go. So that's what the map looks like if it's been filtered to 25 angstroms. And then it uses that to generate the neutral model. Once you're satisfied with the number of points that you got, I know I went over some of this a little bit last week. Once you're satisfied with the number of Gaussians that you have there by adjusting this parameter and this parameter, then you press the train neutral model button, and then that will make the points sort of properly accommodate the actual density map the best it can. This is actually a training step, and it takes a few minutes to run. When you're running it, you would normally want to keep this visible on the screen so you can actually view the console output while it's running. Once you train the neutral model, then you would next train do the actual training of the dynamics, train the Gaussian mixture model. So you would hit train neutral, train that. That'll produce sort of final sets of coordinates for the Gaussians, and then you do train GMM. You would like to have all of these parameters established before you hit the train neutral button. There are a few things that you can change between pressing train neutral and train GMM, but only a few. If you turn on and off the position, if you change the number of latent dimensions, so if you did train neutral and then you say change the number of latent dimensions and then did train GMM, it would fail, it would crash. Because the two neural networks didn't agree on their parameters. So you have to be a little careful about that. So I suggest picking all of these parameters first, then hitting train neutral, and then once you're happy with the train neutral, then you can hit train GMM. There are a variety of choices here that you have to make. Some of these are explained in the tutorial already. You can see the tutorial is a bit of a work in progress, so some of it, still needs some work. You can see the quick theory overview section still has a big to-do in it. But here, it tells you at least, the values to pick for going through the tutorial data set. Just sort of quickly, this is sort of a minimum and maximum resolution to use when it's coming up with a representation of each particle for training the network. What on earth does that mean? So each particle goes into the network and then becomes a point in the latent space, which we don't have here. So if I switch back here, each point that we see, each dot that we see in here represents one particle. To map the particles into this space, we don't want them to be too noisy. So if I have a 3 angstrom resolution reconstruction and I use 3 as a high resolution limit here, there will be a lot of noise in those parameters that go into the network, and you may find that it's sort of smeared out and spread out a lot more than it really should be. So usually you'd like to sort of start out looking at low resolution representations of your data, characterizing all the dynamics that you can at lower resolution, and then move to higher resolutions with new runs up here. So you'd create a run, you do a run with sort of low resolution parameters, and then if you wanted to move to higher resolution, then you make a new run and pick higher resolution parameters here. The resolution that you use here is the resolution that it's used to generate the Gaussians, and it's also the resolution that's used when it's comparing each Gaussian set of Gaussians to each particle on the output side of the network. These resolutions are used to turn the particles into parameters that go on the input side of the network. They don't have to be exactly the same, but usually this resolution and this resolution will be within about a factor of 2 of each other. If you set this to 5 angstroms and you make a tremendous number of Gaussians, and then you leave this at 25 angstroms, you're probably not going to get as very good results. The upper number that you see here is a high-pass filter number. Again, that's in angstroms. And that just allows you to eliminate things like ice gradients and stuff from getting considered in the network. I can't give you one absolute number. Usually this is going to be somewhere between, say, 100 and 200 angstroms, something like that. In some data sets, if the ice is nice and flat and everything like that, you can actually just leave this out entirely, and it won't do any high-pass filter, and it'll all be fine. I would normally recommend putting in something like around 150. If you want, you can play with a manual high-pass filter on some of your particles using E2 filter tool or something like that, and you can sort of decide what the low resolution limit of information that you want to include should be. All right, this stuff is sort of automatically filled in from the refinement run. Even if you have a structure that has symmetry, I would suggest doing a refinement with C1 instead of the full symmetry, so you can really look at sort of the full symmetry breaking dynamics of the system properly. Number of latent dimensions, the default for this is 4. The reason I got 3 here is because I picked 3 when I set it up, because it can make it easier to visualize. But this is sort of the number of independent degrees of freedom in a certain sense. But since the whole system's nonlinear, you can actually have more degrees of freedom than the dimensionality. It's tricky. 4 is just sort of the default value that we normally use. If you find the dynamics of your system is really complicated and you can't accurately characterize it with 4 dimensions, you can increase that number as you like. Fewer than 4 dimensions often causes problems in having the network converge very well. 3 is okay, but 2 is probably pushing things a little bit. Number of training iterations, you'll find that defaults to 10 when you make a new run, and that's probably not really enough for pretty much any project. I would say 30 or 40 is probably a good bet. This is, for those of you who know something about neural networks, this is the number of training epochs. It's basically the number of times that it iterates over the entire data set when it's training the network. I know it says that 10 to 20 is typical. I've with more experience, I would say that 30 or 40 is probably a better choice. But anyway, the model perturbation is basically giving it sort of, so when you start out the neural network, it's starting out with this neutral model as sort of the starting configuration, and then it's looking at variations from that point. You can see that everything here in this neutral space is sort of scaled roughly from -1 to 1. It's not strictly limited to -1 to 1. You can see this is up above a 1, but it's, it goes up to 1.5. So basically, sort of the general length scale of this plot is -1 to 1. The model the model perturbation is at this scale. It's how much variation it should put in the data when it's first training the network to sort of seed the dynamic learning. If you set this to 0, it's going to have a really hard time kind of figuring out the dynamics. It's going to get sort of stuck at this initial structure for a while. So it'll take a lot more iterations, a lot more training iterations to train. Typically, the default value I think is 0.05. I often try to use 0.02 if I can get away with it. That often means that you have to use a few more iterations, but it might make the final plot that you get out here a little bit more clustered and a little bit nicer looking. If you put something in here that's big, like 0.3, which is what was used here, it helps spread things out. So if you're running into situations like this, where you're getting sort of poor training, you could run a lot more iterations. It would probably sort itself out eventually, or you can increase this number here. So that's what I did in this run. I increased this number here to 0.03 that really sort of helped spread things out, but then you have to run a number of iterations to sort of get it to collapse back down to do something reasonable. All right. The other two things you have to consider here are position and amplitude. If you don't have both of the, if you only have position turned on, then the Gaussians will be allowed to move, but they won't be allowed to change amplitude, and vice versa. If you just turn on amplitude, then they'll be allowed to change intensity. So if you wanted to do just, say, ligand binding or something like that, if you think the structure doesn't change itself at all, then if there's you don't expect any changes in shape in the structure, you just expect changes in intensity, then you could just do an amplitude only run. Most of the time you just do position and amplitude, which will allow both of them to vary. All right, yeah, that's sort of a summary of the parameters. Oh, sorry, the one other one is mask. You can specify a file name for a mask file. This has to have the same box size. The mask has to have the same box size as the particles, as the box size that's shown right here. And then that will force the neural network to train only on the Gaussians inside that mask. That doesn't mean the other Gaussians won't move at all. The other Gaussians may move as necessary to accommodate the changes that are observed inside the mask, but it'll focus the latent space on the stuff that's inside the mask. Both I and Muyuan have some plans to sort of make this a little bit more elaborate, so you could have, say, multiple masks and then relate them to specific axes here and stuff like that. But at the moment, it's simple. You can either have no mask or you can have a masked region to consider. All right, so let's take a look at our results. So I ran this Gaussian mixture model with these parameters, and I wound up with this plot. So it's a three-dimensional latent space. That's what I told it to generate. I can specify which axes of the latent space I want to look at as X and Y in the 2D plot here. Now, you'll find that there are actually 3, 4, 5. Oh, sorry, 4. Yeah, so 2, 3, 4. Yeah, so those are the 3 dimensions. So you'll find that there are actually 5 different axes that are available here. So what it does is the axes labeled 2, 3, and 4 are the results of the Gaussian mixture model run. So if I look at 2 versus 3, or 2 versus 4, or 3 versus 4 in this plane, those are looking at the direct results of the Gaussian mixture model. Axes 0 and 1, which are what it starts with in the display, are the results of doing a 2-dimensional principal component analysis projection on the n-dimensional space. So if I did 10 dimensions here, 0 and 1 would always be the sort of a 2-dimensional slice or 2-dimensional projection somewhere in that 10-dimensional space, sort of trying to optimize the differences that are observed. So 0 and 1 will usually show you the sort of the most variation you can find in one plane amongst your data. So let's take a look and see what we've got here. So let me turn off the neutral map and the neutral model, and we'll just look at the dynamic map and the dynamic model here. So if I use my mouse pointer here and I move it around, it will show me the dynamic model corresponding to each of these different points. Okay, so you can see there's this green circle here. This green circle, what it's showing me is the average location in n-dimensional space, three-dimensional space in this point, but the average position in that three-dimensional space of all of the points inside that green circle. So you can see there were 18,000 points. Now you'd say that doesn't look like 18,000 points, it looks like a lot fewer. Well, that's because each point here actually represents a tilt series. So the 18,000 represented here are all of the tilts in the tilt series for all of the points that you see inside this circle. So as I move the circle around, I can see in real time the rearrangements of the structure that correspond to that particular change. Now, something interesting happens when I move up here. You can see this strong intensity change. Now suddenly the intensity down here, these look darker and this looks brighter. So something kind of funny is going on when we get up here. When we come down here, it's actually a very different sort of shape. So this is almost certainly some sort of outliers, particles which shouldn't really have been included in the reconstruction in the first place. Now, how would we figure out what's going on with that in a little bit more detail? So what we're looking at here is just the Gaussian model. So let's find an orientation here where we can see interesting sorts of things going on. So here's the channel through the ribosome, I think. So what I want to do is I'm going to rotate this to sort of put the channel in the plane of the screen, more or less. And this should be a good orientation for seeing kind of ratcheting motion. Okay. Now, you can see there's a list of things over here. Once we've got our points in space, I can run classification on these points. So either I could manually, if I go down here and I say make set, I could manually pick points in one of these two-dimensional spaces and make a set out of all the points that it finds here. So out of, like, say, the 9,000 points that are inside this circle, I could turn those into a set. Here, I can go ahead and do that. Say make set, and I'll drag around here. The circle doesn't show up anymore, but when I let go, you can see some of these points have turned red. So these are now all of the points in this new set that appeared here. There are 21,000 of them. And I could then do stuff with those points. That's one way of making sets. Another way of making sets is to use classification algorithm. Now, I will point out that unfortunately, these three algorithms, which I'm including right now, only work on fairly small data sets. If you try and run it on one of these big data sets that we've got with 100,000 particles or something, it's just going to crash. K-means is sort of the only one we've got in there right now, which will actually work reliably on any size data set. So what I have here, these first 8 sets that appeared right here, are, I set this from 2 to 4. So that corresponds to the axes here. And then I said K-means with 8 sets. Okay, so I said 8, 2 to 4, and I hit K-means. I'm not going to do it again right now. Actually, why don't I do this? I'll go ahead and do K-means in this particular plane. So we'll do it on axes 0 to 1. And I'll go ahead and make 8 sets again, and I'll hit K-means. Take it a second to run. And there we go. We have 8 new sets. And if I click on one of these sets, you can see where it put these clusters in space. So you can see the red points coming up. If I select all of these 8, each set will appear in a different color. Okay, I realize these points are kind of small. I used to have it set so the points got bigger when you did this, but when you make the points bigger, then on the big data sets, they're all overlapping on top of each other, and it's really hard to see. Anyways, you can see that the K-means produced these different clusters of data. Now, once you have the data sets clustered like this, you can then build three-dimensional reconstructions for them with one of these 2 buttons. Now, if you haven't built a reconstruction yet, you have the option of, deleting sets. Once you've made a reconstruction, once I've built a map for the reconstruction, you can no longer delete the set because the map can't be deleted. The map is always there. So the idea is you can pick one or more of these data sets. I could pick all of them here if I want. And now I can see what the clustering looked like here. And then you can either build map or quick map. Okay, what do build map and quick map do? So both of these options will basically take all of the points within one particular set, and it will do a 3D reconstruction of those points. And then it'll save the resulting map. It actually also computes a resolution of each of the corresponding maps. So here there were 18,000 particles in this particular set, and it produced this map with a resolution of 10.3 angstroms. So this is done just by taking the even numbered members of the set and the odd numbered members of the set, and doing an FSC between them when it does the reconstruction. Quick map will downsample the particles by a factor of 2 before it does the 3D reconstruction. The resolution may still come out the same. It actually may sometimes come out appearing to be even better, even though the data was downsampled by 2, just because the artifacts are having more influence. But the key point for this is if you run quick map, it'll run about 10 times faster than if you say build map. So if you just want sort of a quick look at what some of the variations in the data are, you can do quick map, and then that'll let you look at the 3D reconstructions, and then later you can go back and you can hit build map on the same ones, and it will do a more thorough job. These reconstructions run in threads on your machine. So if I pick 8 of these and I say quick map, each of the 8 will run in a separate thread, and it'll show you the progress while it's running in the command line. So you could bring up the shell window again, and when I say build map, you could watch the progress. Actually, here let me go ahead and I'll make a manual one again. So we'll make a manual data set for just these particles up here, and there's 1,000 of them. And then I'll say, I'll say quick map, and then we'll bring the shell up to the front, and we should see, oops, maybe the wrong window. There we go. So you can see thread 0 at such and such a percentage, and when it finishes, we should get an update there, and you can see there's now the average, and it shows a resolution of 6 angstroms. That's again, this is not like a final resolution you'd put in a paper. This just sort of gives you an indication of sort of how self-consistent the set was. Okay, so let's now take a look at the one we just made, and look at what we see. It's just a blob in space. I can open the control panel again, and dynamic map, isosurface. I can lower the isosurface threshold. There you can see it's this funny blob. It doesn't look like a ribosome at all. So these points up here are indeed outliers. They're not good. Now let's say I picked one of these that I already ran earlier. And you can see, oh, look, it's a very nice ribosome particle. All right, so let's see if I can get this positioned in a reasonable orientation. It's actually kind of tricky to get this right. Now you'll know, all right, let me just say what we're seeing here. So now up here, we're seeing the dynamic map, the dynamic model. I can turn off the model, so we're just seeing the map. And you'll note as I rotate, it's also updating this view down here. This is a slice through the center of the map. So basically in the plane of the screen, this is a density slice through that center. I can adjust the thickness of the slice. So now it's a slab. If it's 12 here, that means that it's plus and minus 12. So it's actually 25 planes thick that we're looking at here. And I can also move the center position up and down. So I can adjust sort of what plane I'm looking at here. And it will rotate in real time as you rotate the structure. As a convenience, there are top, bottom, side. These are sort of fixed view buttons, which will rotate to specific fixed orientations just as a convenience. All right, so I want to get back. Let me turn on my neutral model again here. And I want to find sort of that orientation that I had again. It's actually kind of tricky sometimes to find the orientation where the ratcheting is the most apparent. Probably something kind of around here. Okay, so there's the dynamic model, dynamic map. Turn off the dynamic model. And now if I click on one of these, it will switch to the different dynamic maps. And I think the biggest ratcheting change, yeah, 4 to 5. So I didn't quite pick the right plane here. 6, that was the outlier data set. So you'll note when I click on one versus the other, it's going to update this plot in real time. So you can see this is red, and then when I pick 6, now this becomes, oops, not 6, 5. Right, so 5 is red over here, and 4 is red down here. So as I switch between these two, you can see here, if we look at this, you can see this ratcheting motion between the two states. So in addition, and of course that happens unfortunately occasionally, and I haven't figured out exactly what causes it. Sometimes as you're rapidly switching back and forth between the 3D models, something happens with the isosurface generation and it crashes on you. It won't lose anything. We can just sort of go back exactly where we were again. It's just an annoyance. Anyway, so back to what we were doing. So turn off the neutral map. Unfortunately, I did lose the orientation that I had so carefully found. But anyway, so as you switch back and forth between these different states, oh, there we go. I got the ratcheting just right. So there you can see the ratcheting motion. Actually, if you do a little bit more work with this data set, you can actually find sort of dissociating tRNAs and stuff like that. So there's actually 3 or 4 different interesting sorts of states you can find, in addition to identifying this subset of particles here. All right, so this is one example. Let me take a look at another example. Let me see. I think this is we'll take a look at this. This is synthetic data. So what I did with this data set is I took a 3D model of Graphical from the PDB, and all right, you can see the 7 sort of subunits. So if we look down from the top, right, you can count 1, 2, 3, 4, 5, 6, 7. And if you look at it from the side here, you'll notice that this subunit looks good, this subunit looks good, this one looks kind of smeared out. Let me turn off the neutral model. Let me turn off everything. There we go. So you can see how this particular subunit looks kind of smeared vertically. What I did is I took this subunit and I rotated it kind of around this axis. So I rotated it up and down like this into different orientations. Completely unrealistic, nothing to do with any real molecular motion that anything does in Graphical. This was just sort of a test case for doing the Gaussian mixture model. And the goal was to see if we could classify out that sort of motion. So here is the results of one quick test run. And you can see, again, we got this sort of line thing. So like I hadn't refined it quite enough. So this was done with 25 iterations, model perturbation of 2. Here, 40 iterations with a model perturbation of 2, and you can see it smoothed out pretty nicely. So here we go. We got our nice distribution in space. I did classification a couple of different ways here. So I did just sort of a k-means classification on the entire subspace. And then I also made some manual classes here. So here you can see I have these bands through the data. So how did I make these horizontal bands? Okay, what I did is I plotted axis for basically 0 versus 0, or I could have used 1 versus 1. Actually, in this case, it was 1 versus 1, I think, right? Okay, so let me turn this off and explain a little bit more. So let's look at the dynamic model here. Okay, now you can see all the black points. You can mostly ignore those. If I drag over here with the mouse, you can see if I move vertically, that seems to correspond, if you look right here, to the up and down motion that I was trying to characterize, at least predominantly. If I move left to right, it doesn't really. Something else changes a little bit when I move left to right, but that doesn't seem to be accomplishing anything as not the thing I was looking for anyway. So I move up and down, we can see something that looks kind of like the right motion. Now you notice the black spheres don't really move very much. That's because they have basically 0 density. They're mostly there as kind of placekeepers to permit things that are moving to be detected well. So you don't really expect them to move. So I might actually go in here in the sort of the dynamic model and adjust my threshold here so we don't see those just kind of visual distractions. So now as I move up and down, we can see that seems to correspond somewhat, at least, to motions of that domain. Now, maybe if I did an axial thing, that would be better, or maybe this way would be better. I don't know. It looks like this is not too bad. I could also look at some of the other axes, right? I could look and see what axis, say, 2 versus 3 is. And we could see, because somewhere in there, oh, it looks like that direction actually seems to correspond pretty well to the motion too. Anyway, I could pick an axis and I can try and do it. So now if I wanted to make these sorts of bands, that I made with these manual classes here, what I did is I plotted axis 1 versus axis 1, and then I used the make set mode to box out circles in this mode. So it's basically just using a single axis. So then all of the other dimensions are basically getting included. It's only making its classification decision based on the position on this line. Okay, so take a look at the results. So you can see here's the map. And as I move up here, you can see that that's rotating downward. Now, it is possible to do a better job than what we're seeing here. You'll notice that here, for example, we can see this nice 2-helix bundle, which is sort of separated out. But as I move down here, eventually, it's still there for that one. This one, for example, oh no, it's still there. Actually, we're not getting it too bad there. This stuff looks kind of smeared out here, and it looks a lot better in some of these other sets here. At least a little bit better. Yeah, there. So these upper ones, it looks a little bit better. So I guess what I'm trying to say is that some of these sets are still sort of intermixing different subsets of the data to a greater extent than they should. The number of data points in each of the different states was actually pretty uniform in my original distribution. So the fact that we're seeing this sort of fewer points up here and more points down here means that we haven't really perfectly characterized the motion along one particular axis here. But we have at least managed to characterize the motion. If we look at the k-means segmentation, we can look at each of these different maps, and we'll see that a couple of these seem to have sort of pulled out specific orientations. There may be some orientation preference. This is kind of a risk on a smaller data set. This has only got like 8,000 particles in it. So each of these individual maps that we're looking at only has a few hundred particles in it, which means that there's an opportunity for there to be a preferred orientation that's getting classified out of the data. If you have a 100,000 particle data set, then you will tend not to see that kind of thing happening, right? So this one's particularly pronounced, where you can see this smearing out along an axis because it was missing particles in other orientations. Anyway, so this is sort of how the system can work and some of the issues that you might run into. I'll take a look at one more data set, which we started analyzing recently, which is this IP3 receptor data set from Marina Sarasheva's lab. This paper was recently accepted for publication, although the paper didn't include very much of sort of some of this Gaussian mixture model stuff that we're seeing here is new. So basically, this was 3 different biochemical states of sort of an apo state, a state designed to trigger the channel to have a high open probability, and then a higher calcium state, which was designed to sort of then force the channel to close again. So if I run the Gaussian, let me pick one of the good sets. You can see I did a bunch of different runs here. I've got 4 different GMM runs. Some of these were done with symmetry, some were done without symmetry. So we can take a look at, for example, this one. And we can see that the distribution in space, there seems to be sort of a clustering here. If we look at some of the other axes, this was done in the 4-dimensional latent space. So let me look at, say, 2 versus 3 versus 4. I'll look in this space. Now we've got even more clustering going on here. If we zoom in a little bit better, you can see that there. Another way of visualizing this, if you middle click and open the plot control panel, you can actually do a contour plot. And maybe increase the number of contours here. And now you can actually sort of see that there are these sort of local clusters that we observe here. So once you observe this sort of behavior, let me come over here and I'm going to go to a side view, turn off the neutral map and the neutral model. And now if I put a point in space here, we can see the change that corresponds to, say, moving in a particular direction. So you can see here, these domains, as I move here, move up and down a little bit, that sort of thing. I also did classification. Let me go back to my symbol representation here. So you can see I made a bunch of different classes here in various ways. So let's look at, say, set 0 here. That's that particular portion of the subspace. I'm going to turn off the model now, and we'll just look at the map, right? So you can see these maps are actually pretty decent. They're at least at sort of, just sub-nanometer resolution, at least most of them. So you can see the alpha helices here. And now we're looking at a slice through the middle. So this is actually the pore where the calcium ions would go in or out. And if we look sort of up or down here, we can see distinct changes in the shape. Now, again, this is just a slice through the middle. If I make the slice a little thicker, then I can sort of see more of a central projection. But this is just sort of showing what's going on sort of right along the potential ion conduction pathway in some of these different classes. You can see all sorts of interesting sorts of changes going on there, and that some of these changes are then correlated with some of the behaviors that you see elsewhere. Here's another run I ran, and in this run, I used a mask. And the mask that I used corresponded to just the pore region of the channel. So just the alpha helices around the pore, and then sort of the next layer of helices just outside that in the pore region. And you can see this produced a very nice distinctive set of classes in the latent space here. So some really interesting stuff obviously going on there. If I go back down to 0, I think 0, 1, right, you can see this sort of clear kind of clustering that seems to be going on here. Also notice here, I've got these 3 sets up top here, which have 133,000 particles each. So this was a mixed population where I mixed particles from the three different biochemical conditions, all together into a single GMM run. And that this now represents the membership, the particles which were in the original biochemical state. So if I click on 0, those are all of the particles that were in state 0. These are all the particles that were in state 1, and these are all the particles in state 2. So what we're seeing here is how well those different states correlate with different parts of the latent space, where the latent space was generated just based on the pore region. Now, if I go back and look at the other one here, I also had, maybe I don't have the 3. Hang on, maybe I have to pick a different one. Somewhere in here, I also have the 130. Yeah, here we go, like this one. So here, the 130, there was no mask in this one. But again, we can then see the representation. So here, if we look at 1 set, 2 set, 3 set, we can actually see there's more substantial correlations between the distributions in the latent space and the 3 different populations of particles when we don't use the mask. So basically what that's saying is when we just look at the pore region, the changes are much more subtle when we relate it back to the different biochemical states, but there are still some very interesting subclasses going on when we look at the actual data. Anyway, so this is the sort of thing that you can begin to explore now using this tool. There's still a lot of stuff, a lot of development effort that we want to do. There are some really interesting, sorts of things that you observe here. So, for example, down here, when I did the pore classification, I split this up into a bunch of different data sets. Okay, so this was just doing k-means classification on 0 and 1, so on this particular plane. And you can see, for example, this set produced sort of 8.1 angstrom resolution, 60,000 particles. Here's one that's 7.1 with 50,000 particles, and also an interesting state. But somehow, these populations of 37 and 34,000 particles have very low apparent resolution, right? They're something sort of completely different, something messed up about those particles in some fashion. You could say, well, these are just particles that were over a more heterogeneous population or something in some sense, but in theory, they're all aligned really well and that sort of thing. So it's not quite clear what's going on in some of these substates that you see. But this at least gives you the opportunity to generate some of these subsets, and then you could actually, in theory, you could pull out just this 50,000 particles, and then you could run additional refinements on those particles and see if some of the changes that you observe in various places actually hold up once you've refined just those particles in the data set, because this is just using the fixed orientations that were determined when all the particles were refined together. Now, in theory, that's what this save set button is supposed to do, but it doesn't work yet. That's probably the next thing on my list. I should probably make that work sometime in the next few days. Right now, I don't think it does anything. Anyway, so I hope this gives you sort of a flavor for the sorts of things that you can use this Gaussian mixture model to explore in your maps. Everyone's been very silent, and I've just been kind of randomly meandering through this talk. So I will ask explicitly for questions now. Everyone is still very, very quiet.
I can ask a quick question. So when you were talking about, how it's kind of weird that those sets that have, a decent amount of particles but are getting really low resolution.
Yeah.
So are you thinking potentially this could be a way this could be used to then, maybe filter those sets out that maybe are attributing not great particles and then doing, reconstruction?
Certainly it is. I mean, as we saw with the ribosome data set, certainly it is possible in some cases to identify, outlier data sets, outlier sets of particles which should be excluded from the reconstruction. And it's likely that you'll be able to pull out a different subset of particles that way than you would pull out with, say, your Reliant classification results or something like that. So that is a potential use for this. As to what's going on in this specific case, this is something I just noticed a few days ago, and I honestly don't know exactly what's going on here. It seems like these are pretty well-defined classes, and it seems like they kind of ought to have particular features associated with them. So I'm not quite clear on what's going on exactly with these particular particles. So that's something I need to dig into and look at a little bit more. And it's only something that I noticed in this masked data set. So when the classification, when the GMM was run with a mask around the pore region, then suddenly those outliers popped out. When I did the classification here, and still see, sort of this nice, interesting structure, I didn't see the same sort of thing happening at all, right? So I mean, there is this data set which is only 13, but you can see even that, the 13 still at least looks like it has sort of the right shape. And certainly there is a little variation in sort of how homogeneous these different data sets are. Right. So, this one, which gets to 5.7, you can see it's a little, sharper looking. I mean, this is getting somewhat filtered up here based on the determined resolution here, 9.4. Anyway, I don't have answers to a lot of questions yet. One of the things that we need to do is have some better strategies for doing some dimensional reduction to try and better visualize some of these subspaces. If it's a three-dimensional space, it's fine. We can do visualization of three-dimensional points pretty easily. But if it's a higher dimensional subspace than that, then without dimensional reduction, it's kind of tricky to really see. What you're seeing is actually projection. So if I look at these class like this here, and if I look at that in a different projection orientation, it may not look nearly as, well, apparently this one does. Some of them won't look nearly as isolated in space anymore. Let me try a four-dimensional space and see what I get with one of those. Always seems to happen, right? Right, so you can pick a cluster like this, and it looks like it's just kind of randomly spread out across space. But if we pick different axes to look at it in, you can find out that it's actually better confined than it seems. So in the four-dimensional space, it's actually a cluster, but in these two-dimensional projections, it looks like it's overlapping with lots of other stuff in any particular orientation that you're looking at.
So Steve, is it possible this analyzer is able to study any particles or features without a certain structure? For example, like a membrane.
Well, I mean, if you want to look at, for example, the other example I often use is, like the in situ nuclear pore complex, where there's a lot of variations in the membrane thickness as it approaches the NPC. That sort of thing looks fine, but you have to have some sort of a fixed geometry, right? So when you put the particles into this, the orientations already have to be determined in some self-consistent way. They don't have to be perfect. They just have to be self-consistent. So if you put in a bunch of particles all in different random orientations, then the Gaussian mixture model is sort of mostly going to be spending its energy on trying to get the orientations to agree with each other instead of looking at variations among the particles. So, starting out with a refinement where you've put all the data in and you've determined some orientation for each particle that agrees in some fashion is an important entry point here. We have done some playing around with using the neural network as a strategy for determining particle orientations. So there's actually an option that you can use in the command line program, which lets you, once you've built up this dynamic model of the particle, you can then redetermine the orientations of the particles in the context of the dynamic model. You imagine if you have some big domain which is moving, that may influence the orientation you determine for the particle. So you may be able to come up with more self-consistent orientations if you consider the orientation in the context of the dynamic model. So you can do the GMM to determine the dynamics, and you can go back and determine better orientations, and then you can do the dynamics again, and you can iterate back and forth with that a couple of times. And there are some ideas for maybe actually using this as just a whole refinement strategy. So you basically put in a bunch of Gaussians, and then you refine the Gaussians against the raw 2D data and sort of determine the orientations and the Gaussian locations simultaneously and that sort of thing. But that's a much more challenging deep learning kind of training problem. So that's kind of a future research project, not something that exists now.
I see. Thanks.
Okay. Anyone else? Any questions? I realize the tutorial for this is still sketchy. I'm going to continue working on it over the next month or so, and the program is going to continue to evolve. Phil?
Yeah, thank you for the nice lecture. It's very beautiful and it raises all sorts of interesting ideas and questions. But my question's very perfunctory about something irrelevant. But since you're here and leaving soon, I'm thinking of creating some instructions for something I'm doing, and I'm wondering, am I able to put it off of the EMAN pages but sort of hidden so that it won't won't come on a web search. And would you mind if I did that?
Well, if you make a page in the wiki and you don't link it to anything else, then the only way you could find the page would be by doing a full text search or something like that.
Okay. So you don't mind if I do that?
No.
Okay.
You're
Okay.
welcome to put anything that you find useful as long as you
Right.
recognize the fact that people could potentially find it.
No, I won't link it off of anything. I just
No, I understand. But if someone did a full text search, then they could potentially find it, right?
there's a way to hide it from Google searches too, I think, but
There probably is a way to hide it from Google searches, but that won't hide it from the wiki's own internal search engine. If someone
I see. I see. Okay.
So
Okay,
it won't,
thanks.
you can't really have something that's private in the wiki, but you can have something that's not easily
Okay.
accessible.
It'd be super useful as I write some software to, if I show it to someone, I can bring up the wiki and say,
No,
explain.
sure.
Yeah. Okay. Thank you.
Okay. All right. Any other questions?
Then how do you create a movie to visualize the motions?
Well, basically, you'd have to take the maps and then use whatever movie tool you prefer to make a movie out of the maps. So you can see that one of the things that's shown here is map number. So you can see that these map numbers get pretty big. So these map numbers, just every time you do a new build map, that map number gets incremented by 1. And if we go to the command line here and E2 display, so this is actually probably useful. So if we look inside that GMM01 folder, you'll see that there are a bunch of files for each of the labels. So here's the 3D one I did. Here's the one I did with the pore mask. So let's look at the pore mask one, for example. So you can see there are a bunch of different files here. So this encoder and decoder file, this is the actual neural network itself. The pore mask mid. So the mid is the output from the for each particle for the trained network. So there were 399,000 particles, and there are five columns in this data. The first column is just a number. Just the sequence number of the data. So then it's got 4 columns, which are the latent space vector. There's a different one here called AUG, stands for augmented, which has the extra 2 columns, the 0 and 1 column, which have the PCA projection into the subspace. So column 0 and column 1 of the PCA projection here, I can actually do plot 3D on this. Of course, it's 400,000 points, so the plot is not super fast. Let me make these tiny. Sorry, it's drawing 399,000 points, so it's really not going to be very fast. Huh? Sorry, it should be faster than that. Oh, maybe it didn't get... Alright, not quite sure why it's not decreasing the size of the circle.
By the way, Dr. Ludke, I linked to, I feel like you discussed making movies, or at least visualizing it in the GMM tutorial you did, a few weeks ago. So I linked to that in the chat for anybody that's interested.
Ah, okay, fine. I'm not sure why the size is not changing. Anyway, you can pick the axes and stuff that you want to visualize. This is obviously just too slow to be workable with 3D space and 400,000 points in it. There's also a command line program you can use to further augment this. If you want to do other dimensional reduction algorithms, you can add more columns to this augmented line and have them appear. Anyway, the thing you were asking about, which is the reconstructions. So if you look through here, you can see pore mask, oh, sorry. So the reconstructions aren't specific to a particular run of the GMM. So if we look down here, we will find, oh, where is it? Projections in, set even, split, particle subset. Where is it? So I'm just looking for the maps. Oh, there we are. Set even, set odd, set maps. So this file, it has 204, 220 by 220 by 220 volumes in it. You can see it's actually not very big, and that's because it's using compression on these volumes. So if we hit info here, we can open up that list, and the different subvolumes in this list correspond to those numbers that we see in the GUI. So I can double click on or show 3D. I didn't pick a very good one there, but that's fine. Right, so you could open up a bunch of these simultaneously if you wanted to, and then interactively scroll through them like this, or you could load them into Chimera. You could make a Chimera movie, however you want to do it. All of the basic. So, but I'm just saying, basically, all of the maps that you created are going to be saved in this set maps file.
Okay, thanks.
Yep. Okay, any other questions? All right, great. Well, feel free to email me if you have any questions that I didn't manage to cover today. I realize there's still quite a lot to understand if you want to really make profitable use of the GMM stuff. But if you've got a project where you've run an EMAN refinement, or you could take a Reliant project and you could convert it to EMAN, you can give it a try and sort of see what sorts of results you can get out of it.